we now come to beats and the Doppler effect. And the idea of beats is fundamentally when you have two or more signals that have slightly different frequencies. So up until now, we've either been dealing with signals that have the same frequency or have integer multiples of each other in the cases of standing waves on strings and so forth. But here we can have two generically different frequencies, right? So let's let the blue be frequency 1 and the red be frequency 2. Okay, so the blue in the top picture is frequency 1 and the red is frequency 2. And because our axes are in positions and times, we can actually get an estimate of which of these signals has a higher frequency. And so you'll note that the blue has a crest here, here, and here, whereas the red has a crest here, here, and here. And you'll notice that those are more spread out than the blue ones are. And maybe perhaps we should use the individual colors. So our first blue crest is right here, here, and then here. And then for the crests for the red signal, you can see that they are a little bit more spread out. Okay, so the entire issue here, and we say that to say this, that in this particular example, frequency 1 is greater than frequency 2. This is not in any way, shape, or form a necessary statement to make. It's just for our observations for this particular example, right? But what we can see here is that in this region and in this region, the signals are almost lined up. But then as we get to this region, okay, so the signals here are lined up, but then when we get to this region, the signals are spread out. And you'll just continue to see this pattern. They line up, and then they're spread out, line up, spread out, line up, right? And so this is, as the signals are overlapping each other, you will consistently and always hear, if we're referring to sound waves, the signal that you hear will be the superposition of these two waves at all times. But because when our signals are lined up, this is constructive interference. And when they're spread out, this tends to have destructive interference. Your signal will modulate between a higher amplitude when the signals line up and a lower amplitude when the signals or destructively interfere. Now, your signal might not ever go to zero if your signals have different amplitudes. In the case of when the signals have the same amplitude and they destructively interfere, you will see the sound go to zero at these points at complete destructive interference, but you'll have maximas at the points of constructive interference. Okay? So, how do we analyze this? Okay? So, suppose we have a signal that looks like this. Whoop. Let me write it like this. Let me put it down here, so we're not constrained for as much space. Okay. So 2 pi f omega, or I'm sorry, 2 pi f is omega. So your argument is the same thing as we've been writing down before, kx minus omega t. Okay. And then y2 is going to have amplitude a2 times cosine k2x minus 2 pi f2t. Okay? All right. So, when we add these together, when you add two cosine signals together, the result, cosine u plus cosine v, is equal to 2 times cosine u plus v over 2 times cosine u minus v over 2. Okay? And so what happens is, if we assume, for the moment, our amplitudes are the same, okay? If our amplitudes are the same, then we can write this as ny2 so then when we add these, whoop, right? When we add these, we can factor out the amplitudes, and we're left with the sum of our cosines. And so now we employ this rule, that the cosine of u plus cosine v equals 2 cosine u plus v over 2 times cosine u minus v over 2. It's a mouthful, but the result is a times 2. Now, what we're going to do, okay, is we're going to take a snapshot when x equals 0. Okay. And the reason we're going to do this is to make the problem just slightly more tractable mathematically. But what we're setting that equal to 0 is okay, because we could put it to whatever time or position we like, rather, and we would still find the same result we're about to find. It would just be in a slightly more complicated form with our position variables. But the time dependency is really what we're after. And maybe I should have specified that beforehand. And if we come back here, we can kind of see that because this is the time domain, our points of constructive interference occur in time. Okay, so that's why we're interested in the time domain of this calculation. So the idea being that this phenomenon where you get a louder sound and then a softer sound and then louder and then softer, this is time dependent. So that's why we're interested in keeping t as a variable and evaluating what's going on at a specific point in space. Okay, so we take our snapshot when x equals 0, and what we find is that at that point the minus signs don't really matter because, well, they just don't matter, and we'll see why here in just a moment. But so we have 2 times our cosine of u plus v over 2, which is going to be this plus this over 2. Okay. But 2 pi f1t plus 2 pi f2t is equal to 2 pi times t times f1 plus f2. And then when we divide that by 2 from here, okay, this is just the average of the frequencies. Okay. So, and the reason the negative sign doesn't matter is because cosine of negative x is the same thing as cosine x. Okay. So when we set x equal to 0 here and here, then I get cosine of minus 2 pi ft, which is the same as cosine of 2 pi ft. So the negative signs don't matter. Okay. And so this is now cosine of 2 pi times the average of our frequencies times t times the cosine. Now we take the difference between our frequencies, or the difference of our arguments rather, and 2 pi f1t minus 2 pi f2t as per this calculation right here. This is 2 pi f1 minus f2 times t, right? And because the cosine always returns a positive, well, it doesn't always return a positive number, but it returns the same number between negative and positive arguments, we also therefore can put these in an absolute value sign, and we do not lose any generalization. So this is 2 pi times f1 minus f2. And so this just ensures that It doesn't matter which one is bigger, F1 or F2. All you're really interested in is what the positive difference between them is. And then, of course, that gets divided by 2. So, this is time dependent. This cosine part of your expression is time dependent. But this is also time dependent. And what happens is the 2 comes out front. And we also pull this portion out front. And then we have cosine of 2 pi f average t. And so you have 2 cosine functions running through here. Okay. And one of them is the inner portion. One of them is this part of the signal right here. Okay. The other one is the envelope. And what we mean by the envelope is this. There is a cosine function, or at least a sinusoidal function, running through here like this. And it will have a frequency equal to your beat frequency. Okay? And your beat frequency is this right here. Okay? And so, well, let's come back up here. You'll also have your envelope kind of bounds everything. Right? But you can see that this has a wavelength of this. But lambda equals your velocity over your frequency, or V equals lambda F, right? And so there's a frequency that's associated with this. And this is your beat frequency, okay? So the frequency that's associated with this wavelength is your beat frequency, right? And so what this means is that we consider this to be the time-dependent cosine function running through your signal. And then this is your amplitude. But as you can see, your amplitude is time-dependent. Okay? So your beat frequency is the frequency with which it takes for your beats to line up. And this is why we call it a beat frequency, is because if you have 2 frequencies that are extremely close together, it actually sounds like a beat. It sounds like if you were to hit 2 tuning forks and they were slightly off of pitch from one another, you would hear like a kind of sound. Okay. And so it's that pulsing that we call beats. Okay, so this is your, or the reason we have beat frequencies. And so, why is this useful? Well, one of the most practical applications for this is tuning instruments. When you have two instruments that are perfectly in tune with each other, you will not hear those beats. So guitar players use this when they tune, if they're going to tune without an electronic tuner. And they tune, to whatever the lowest string is, and then they tune the next string up from that. They will put their finger on the fretboard on the lowest string until it's supposed to match the note of the next highest string, and then they pluck both of them together, and they'll adjust the higher string until it has the beat frequencies removed. It has that kind of nee kind of sound removed, and you only hear both strings giving a pure tone. Can't really mimic a guitar string, so forgive me, but that's the whole point. Piano tuners use this as well, as do other musicians. But it crops up all over signal analysis. Okay, so if you're ever going to go into any sort of signal processing, or you have to do any sort of signal processing, you are going to be working with beat frequencies a lot. Okay, so that is beats. This is how you calculate the beat frequency. Okay. And next up is the Doppler effect. And so, with the Doppler effect, the entire idea of the Doppler effect is, how does the pitch of sound change if things are in motion? Okay. Now, you have multiple things going on, okay? But, so for the moment, imagine a stationary siren giving off sound waves, and these represent the crests of the sound waves, or the points of compression, if we're going to be very precise. Okay, so let's say this is a siren, and I put an observer over here. And I put another observer over here. Okay, now if both are stationary, if this is true, they both hear the same tone. Now, if one of them is closer than the other one, they might hear a different loudness, but they will both hear the same tone. Okay, but watch what happens do 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 do. What if observer A walks toward the siren? Okay. Well, in that case, in that case, because observer A is now moving toward the siren, what they will see is, let's draw it here, A's perspective. because they're moving into the sound waves, they will experience each crest at a faster rate than observer B being stationary will. Stationary with respect to the siren. Okay? So from A's perspective, the waves are more crunched up. Or to be a little bit more formal, the waves are compressed. Okay? So our waves are compressed, and what that means is they hear a higher frequency. They experience more crests per unit time, so they hear a higher frequency. Now, the entire thing with the Doppler effect is this is true if the siren were in motion and we remained our observer stationary. Okay? So if our siren were in motion, then the waves coming out, let's let the velocity of the siren be this way. They're going to be moving into their own waves, and the waves are going to get compressed. But the waves on the other side, they're moving away from their own waves, and so these waves get stretched out. And so observer A and observer B both hear frequencies that are different than the frequency that the siren is actually giving off. So the frequency that A hears is different than the frequency of the siren, is different than the frequency of B. And in this particular case, if the siren is moving to the right toward A, then the frequency that A hears is going to be higher than the frequency of the siren, but that is going to be higher than the frequency that B hears. Okay? So we have multiple frequencies going on, and then we have multiple velocities. So what we say is that both A and B are observers. And at this point, we're going to stop using S for siren and we're going to use S for source. So V sub 0 is not V naught. This is now the velocity of the observer. And Vs is the velocity of the source. Okay. Now, there are multiple ways that you can go about this, and partially because either or both of these can be in motion, and they can be in motion toward or away from each other. But the formulas that we're about to write down, we're just going to justify on the basis of the arguments that we've just made. Okay. There are formal derivations for this, but we're going to table that for the moment and just give you the punchline. But this, what we're about to do should make some sense. But we also have a third velocity to deal with, and that is the speed of sound in the air. Okay, so we have three velocities to deal with. But the velocity of sound in the air is a constant, but it still appears in the equations. Okay. And so, again, if the velocity, okay, so let's just look at the velocity of the observer, okay, relative to the source. Right? Um, if the velocity toward of the observer toward the source, or of the source toward the observer, if that is the case, if they're approaching each other, then well, let's put it this way. If the source then the frequency that the observer hears is higher than the frequency of the source, as if it were stationary. Okay, so Fs is the frequency of the stationary source, and Fo is the frequency the observer hears. Okay? So if they're approaching, then the frequency the observer hears is higher than the frequency of the source, and that's evident from this part of our diagram. But if Fo, if the source and the observer are moving away, keep wanting to write frequency. If source and observer are receding, then Fo is lower than Fs. Okay? And so, if we're going to take the source as the thing that's moving, okay, so if our source is moving with velocity Vs, then our formula has to give a frequency that is higher for the observer than the source. So, what this turns out to be is the ratio of the observer to the source is equal to the speed of sound in air divided by the velocity in air minus or plus the velocity of the source. Okay? Take the minus if approaching, take the plus if receding. Okay? And so the frequency of the observer is then equal to the frequency of the source times the velocity in air divided by the velocity minus or plus the velocity of the source. Okay? But if the observer is the one doing the moving, then again, if it's approaching the source, our frequency has to go up. And so, if they're receding, then the frequency has to go down. So these equations are for if the source is in motion. If our observer is in motion, then the ratio of the observed frequency to the source frequency has to be equal to the velocity in air plus or minus the velocity of the observer divided by the velocity in air. Okay. So that means the frequency that the observer hears is equal to the frequency of the source times the velocity in air plus or minus the velocity of the observer divided by the velocity in air. And so this one, we take the plus if approaching, and we take the minus if receding. Okay? And so if we put all of this together, then it turns out that we can generalize these two results. Okay? And we can write this as one expression. Whoop. I don't need a ratio. Okay. So this equation takes both the motion of the source and the observer into account relative to some stationary origin. Okay. And take the top of your sines if your observer and source are approaching, and take the bottom sines if receding. Okay? So, if we do an example here, okay, suppose we've got a truck and it has a siren on it. And it is moving with a velocity of, let's say, 30 meters per second. A little bit over 60 miles an hour. Okay? And I have an observer that's stationary, and the sound, the frequency of the source, if the siren were stationary, let's say it would have a frequency of 440 hertz. Okay? What is the frequency of the observer that the observer hears? Okay? Well, since my velocity for my observer is 0, if I go to my formula, and by the way, we're going to assume that the speed of sound in air is 343. So, whoops, this is plus minus. Top is plus minus. Bottom is minus plus. Okay? So, because our velocity of our observer is 0, this part doesn't matter in this particular problem. If our velocity of our person were non-zero, it would matter whether they were moving in the same direction as the truck, just not as fast, or if they were moving toward. Okay, so you would take the plus v naught in this case, and this would be minus v naught in this case. Okay. But these signs are not these signs. Okay. Those signs are standing alone. All right. Actually, is that true? Scratch what I just said. Okay. Scratch what I just said. Do. Oh yeah. If that's the case, no. Yeah, if that's the case, this would be plus and this one would be minus. That's right. That's right. So if the observer is moving toward the source, the siren in this case, then both of these velocities are positive. And if the observer is trying to move away, even if the source is catching up to it, then you have to take the negative for that. That's correct. Okay. But we don't have to worry about that because our observer is stationary in this case. All right. So that reduces our formula to and we want to take the minus. And so now we can plug in. So this is 343 meters per second. And notice that this ratio is unitless. Velocities divided by velocities is unitless. Whoops. This is 440, not 343. This is 343. So yes, this has units of hertz. This is a ratio of speeds, so your meters per second cancel out. And now it's calculator time. So if we take 440 and multiply that by 343 and divide that by 343 minus 30, 482. So, our frequency for our observer is going to be 482 hertz. Okay, so it'll be a little bit higher than the frequency of the siren. The reason you can absolutely hear this with sirens, especially with emergency vehicles, as they tend to travel at higher speeds a lot of times than typical vehicles do. So you can absolutely hear this effect when you hear emergency vehicles. You can definitely tell if it's approaching versus receding. Number one, it will be getting louder because you're going to be experiencing a larger energy, a larger intensity, right? Energy per unit area. Your eardrums are going to have more energy imparted to them from a closer siren than it will a distant siren. So you can tell by the intensity that is gaining as your siren is approaching, but you can also hear the pitch of the siren increasing. And then as the truck passes you or the cop car passes you or whatever it is, you will actually hear the siren decrease in frequency. Okay. So, that is a brief introduction to um, beats and the Doppler effect. And for our purposes, that will wrap up sound. Up next is thermodynamics.